Okay, so we used the scatterplot command to look at the data, and can't see much unless I expand it. And it's, yeah, so we've got prestige, logged income, education, proportion women, and we can see we can see these relationships between all pairs of these variables. So that's all fine. Then this is our model we decide to fit. We decide to fit a model predicting prestige from education, logged income, proportion women. And we call it prestige.mod. And let me, if your R is behaving like mine and you're getting these annoying warnings, graphics off can get rid of them. So like if I run it again, you see I don't get the warnings. And we look at our model summary, and let me give that a bit more room. So yeah, our intercept, negative 110, as we discussed last week. I think it's not a very meaningful number because essentially it's the predicted value from our model when all these other variables are 0. But there are no cases in our data set where education is 0 or logged income is 0 or women is 0. There might be. I don't know. I haven't checked, but probably not though. So the intercept is not super meaningful. However, we need it to fit the line to minimize the sum of squared errors. So we're going to intercept. We've got a slope on education, a slope on logged income, and a slope on proportion women. So how do we visualize the fit? Okay, so this is the stuff I'm going to run through pretty fast. If you look in on B courses, in files, tutorial material, no, section materials, there's another hints document, tutorial 3 hints document, and it goes through all this stuff in a lot more detail, like what these plots are doing. And to finish exercise 3, you'll probably need to refer to that document, just because I do want to go through it fast. And we might have more time later, but I just want to quickly get to the part where we're talking about dummy variables and categorical variables. So the first one is just the fitted values. What's a fitted value? You know that jargon, right? Like if I run a model, if I fit a model, what then are the fitted values?
Predicted y values.
Yeah, exactly. So they're the y hats, right? So I run this model, I have maybe 100 cases, and I fit a model, so I have a prediction now for every case. And that prediction is the fitted value. So you can think of them as the model predictions for each case. And those predictions are a linear function of, for each case, of their scores on education, logged income, and women. So you can just imagine like, I take one row of my data and I do intercept plus 3.73 times whatever this row the score is on education plus 9.32 times whatever their score is on logged income plus 0.04 times whatever their score is on women, and that's their predicted value, that's their y hat. So those predictions for each case are our fitted values, and you can get them with this fitted function. So you can see these are all the cases in this, these are all the rows, and this is just the values that our model predicts for those cases. Now prestige, $prestige, what is that give me? So if the fitted values are the y hats, prestige, $prestige is what? Yeah, I think you both said pretty much the same thing, which is that it's y. It's the true values of the outcome. So what this plot's going to show is the fitted values and the true values. And if our model was perfect, what would this plot look like?
Straight.
Just a straight, yeah, exactly, a one-to-one correlation. And if our model was rubbish, what would it look like? Yeah, it would just look random, right? So like we run this, and we can see, yeah, definitely if for the ones where we predicted a higher value, they're the ones that really have higher values. and vice versa. When we predicted lower values, they definitely have lower values. It's not a perfect straight line, but I mean, you could go your entire career probably and not fit a model where your predicted values were this close to the true values. Question?
I was wondering how you got all of the typesetters and bookbinders data loading in your console.
Oh,
You ran to get that.
yeah. All I did was I selected the fitted parenthesis prestige mode,
Oh,
and that just gives me that vector of the predicted values. Prestige $ prestige gives me the vector of the true y values. So this is this is just showing y hat and y. So y plotted against y hat, and it sort of shows that the model's pretty good because there's a pretty strong relationship between them. So exercise 1 is really easy. It's add a y equals x line to your plot using the AB line command. So we've seen AB line used to plot vertical and horizontal lines, right? So we know V equals 40 is going to give me a vertical line, and H equals 40 gives me this horizontal line. But what we want is a line that it just goes x equals y, so a straight line diagonal. And the way to do this is AB line takes, you can give it like a single value if you just want vertical or horizontal, but you can also give it 2 values. And those values will represent an intercept and a slope. So you're basically telling it to plot a line based on an intercept and a slope. So what would my intercept and slope be for an x equals y line? Exactly. 0 and 1. And you can see, well, you can't see it that well, but it's there. Maybe I'll make it red. Yeah, so that's exercise 1. It's a very easy exercise, but don't be fooled because exercise 2 is a doozy. Okay, so try some fancier plots. Now I'm going to speed up. So leverage plots. Look in the hints document about this. This is essentially showing you the unique relationship between each of your predictors and your outcome. And how do we get there? How do we get that unique relationship? Well, essentially what these plots do is they're plotting one set of residuals against another set of residuals. Residuals just meaning errors. So for this plot in the top left, for example, we see education bar others plotted against prestige bar others. All it's done is it's predicted prestige from logged income and women, and then saved the errors of that model, right? So now we're now looking at the part of prestige that we couldn't predict from income and women. So the part of prestige not explained by income and women, and then we do the same for education. We predict education from income and women, and then we plot the residuals against the residuals. So it's the relationship between the part of prestige that we couldn't explain from income and women, and the part of education that we couldn't explain from income and women. Theoretically, it's showing us now the unique relationship between those variables. And it's called leverage plots, which is a bit confusing because you're going to see there's another kind of leverage plot that we also show. Look in the hints document, we recreate this one, I think, just manually by doing exactly what I said. Predicting prestige from the others, predicting women from the others, and then plotting the residuals against the residuals. So hopefully that helps build intuitions. Okay, residual plots. Slightly different again. Now all we're doing is we are plotting the residuals from our model, just our errors from our model. For each case, it's the y minus y hat. Against each of our predictors. So this is education, and this is, so for you, and what we're looking for here is 2 things. One is a really long word called heteroskedasticity, and all that means is the variance of these, so is there sort of dispersion around 0, or just dispersion in general, roughly the same for all points of education, right? So if you saw, for example, there was a lot of variation in the errors here, but then the errors, there wasn't so much variation there, that would be what we call homoscedasticity. No, we want homoscedasticity. That would be heteroscedasticity, which is the bad thing, which makes sort of some of the way we compute standard errors and p-values not valid, because the way we get to our p-values, we have to sort of assume homoscedasticity, which assumes that the variance is roughly equal at all these points. So here, for example, it's like, this looks like almost like a bit of fanning, maybe a violation of homoscedasticity. And then if you saw like extreme violations of it, you might be worried about it, you might not be worried about it. Like there's other kinds of models, there's other kinds of methods of statistical inference that don't assume homoscedasticity. So then you might revert to those. But apart from exercise 3, like I doubt that's going to come up again in this course. Okay, so the plot command actually gives you a few different plots, and you have to now come down here to the console and press enter to see them. So the first one is residuals versus fitted values. This is going to help us again identify homoscedasticity or heteroscedasticity. The next one is the normal QQ plot. This is a bit hard to explain, but essentially another assumption that we make is that our errors are drawn from a normal distribution. So if you're drawing from a normal distribution, your distribution doesn't have to end up perfectly normal, right? But you want it to look pretty normal. Like if your distribution just looked kind of uniform, you might start to suspect, I don't think this data was drawn from a normal distribution. So essentially, this plot is just telling us how well our residuals resemble a normal distribution. And if our residuals were perfectly normal, you would just see a straight line here. And if there's major violations of that assumption, you will see like systematic deviations from that line. And nobody really teaches you how much of a deviation on a plot like this is worth worrying about. So yeah, like good luck with that. I mean, yeah. In practice, I can tell you that most practitioners, most researchers don't pay much attention to stuff like this. They probably should, but it's also very ambiguous how much of a violation is enough of a violation to like actually like make incorrect inferences. So yeah, it's a bit of a inexact science.
Do the theoretical quantiles on the bottom correlate to like z-scores or standard deviations, or is that just like an arbitrary thing?
No. So yeah, good question. Yeah. So essentially, the theoretical quantiles, and I was going through this earlier. The way it works is, so standardized residuals are our z-scores. Like our errors z-scored. So our errors divided by the standard deviation of the errors. The theoretical quantiles are basically if you take one of our errors and you show that it's at the 13th percentile, right? In a perfect normal distribution, we know what value should be at the 13th percentile, right? If our distribution of residuals is not normal, the residual at the 13th percentile might not be in the same position as the 13th percentile of a perfect normal distribution. So this is all that's showing is like, if this case is the like first percentile, where is it in terms of its like observed z-score, and sort of where should it be in terms of the perfect normal curve? Like I said, this is after I've explained that, you can probably forget that now. But that's just what that plot does. This again is very similar to the first one. So this is just the standardized residuals now. against the fitted values. Again, just you're checking it for heteroskedasticity. And the final one, residuals versus leverage. Leverage is just sort of how influential a case is over the regression coefficients. So this is sort of now you're looking for outliers or very influential cases that might be really having strong effects over your conclusions that you might want to think about excluding for different reasons. I guess before we move on, no, it's all in the hints document. Maybe it's worth, okay, so, no, let's just move on. Actually, let me try to explain this. The leverage plots, no, the residual plots are useful, not just for assessing heteroskedasticity, but also for assessing if we fit the correct model. So remember we logged income because we saw that it had this nonlinear relationship with prestige, and we wanted to make that relationship linear, right? Why did we want to make the relationship linear? Because essentially when we build our model, we're making the assumption that we are like more or less accurately capturing the relationships between these variables. And if a relationship is nonlinear and you're specifying a linear relationship, which is what a linear model does like this, you're sort of what we call misspecifying the model, and you can get misleading results. So if you go, I'm going to open up the hints document and I sort of just demonstrate what happens if we, actually I don't even have to do that. No, let's do it. Sorry, I'm very, let's see, where is it? Oh, it's not even there. Okay, so let me just find the hints. All right, where is it? Yeah, this guy. Okay, so this is what happens if we don't log income. Now, you see how we've now got this sort of blue curved line, and it seems as if, well, at low income levels, most of the residuals look negative, and at medium income levels, most of the residuals are kind of positive, and then at high income levels, most of the residuals are now negative. And now think about why that happens. So this is non-logged income and prestige, and this is a straight line through that data. And sort of because we have this non-linearity in the data, when we fit a straight line through it, we introduce this non-independence between the values of X, the income values, and the residuals. Because look what happens. At low values of income, we see these negative residuals. At medium values of income, we see these kind of positive residuals. And at high values of income, they go negative, right? So because we haven't properly modeled that shape, we've got this weird situation in which we have the residuals kind of start off below, go above, and end up below. And that's what these plots can sort of show you. Are you misspecifying the relationships between those variables? Are you missing some kind of non-linearity that's going on that you should model if you want more meaningful coefficients and more accurate inferences? So yeah, that was just a quick digression. Didn't take too long. Glad we did it. Okay, so now we're going to get to the sort of important part of this tutorial. So the LM can also be used for predictive variables that are factors, also known as categorical or nominal variables. Because why have one name for something when you can have three, right? So a factor is actually an R-specific term, factor variable, and I guess it probably comes from psychology, where we talk about different factors and analyses of variance and stuff like that. But essentially, all you have to know is that a factor variable is a categorical variable. It's a grouping variable. So, for example, in the prestige data set, we have prestige. We have type of profession. So it's blue collar, white collar, and professional. And there's no easy way to sort of make this into a number, right? We can't say that, blue collar is worth 1, white collar is worth 2, and professional is worth 3. We have no basis for like putting them on some numeric scale like that. We just have to treat them as these discrete, unique categories. But we can still use them in our models. So as we said, it's a factor variable, and class is a very useful function in R to tell you what kind of variable you're working with. Factors have levels. So in this factor, the three levels are the three groups, which are blue collar, professional, and white collar. And now we can sort of see using this code, this is the mean prestige for each level of this factor variable. Is that clear? Are there any questions? Factor variables. Okay. So now the problem that we have is, how do we use factor variables in linear regression? You guys probably know, but dummy coding, exactly. And what is dummy coding?
Assigning to each categorical variable and then
Yeah, exactly. So dummy coding is the way we convert these discrete groups into numbers that we can use in a model. Because if we just tried to fit a model using words, there's no way to fit a model with words. And like I said, there's no easy way to put them on a numeric scale. So what we have to do is convert them to what we call dummy variables. So now, the way dummy variables work is they're numeric variables, and they work in a linear model just like any other numeric variable. However, they're very kind of special kinds of variables because every single dummy is it can only take two values, 0 or 1. So how many dummy variables do we need, for example, for the type variable in order to kind of tell our model that there's three discrete groups? There's three categories, right? So we need how many dummies? What was that? Three.
Yeah.
I tried to get you to say that, but it's wrong. You always need one less dummy variable than the number of groups, and I'll explain why. So for a three-category variable like this, we only need two dummy variables in our model. So 3 categories equals 2 dummies. And that's essentially because one of these groups becomes the reference group, right? And we can identify the reference group because the reference group will be 0 on both our 2 dummies, right? So if we say blue collar is the reference group, we now need a dummy to indicate membership in the prof category, and that will be equal to 1 for any case in the prof category and equal to 0 for everybody else. And then we need another dummy to indicate membership in the white collar category, and that's going to be 1 for anybody in the white collar group and 0 for everybody else. Now, can you sort of see how once we've got those 2 columns added to the data set, just those 2 dummies, we can identify 3 groups, right? Because blue collar are 0, 0, prof are 1, 0, and white collar are 0, 1. So just with those 2 dummy variables, we can now sort of differentiate these 3 groups. So one way to see this is, I think the command is contrasts. Yeah, so if we go contrasts, prestige, $type, this sort of just shows you, for a given factor variable, these are the dummies that we'll come up with, prof and WC, and these are what the cases will score. So blue collars will be 0, 0, profs will be 1, 0, white collar will be 0, 1. And you should, like R is going to do a lot of this for you, right? Like you can just throw type in a model and you'll see two coefficients pop up, right? So let's just do that real quick. So like simple model, we've got this in the code. We can do a one-way ANOVA, which basically just means a linear model predicting prestige from type. And all we put in the model is type, this three-category variable. But you'll see in the summary, what we get is an intercept, a slope on type prof, and a slope on type WC. So these slopes give us the name of the predictor and the specific dummy. So this is the prof dummy, the name of the predictor, and then the specific dummy. So this is useful. This is really useful for thinking about this. So now, this is our model, essentially. So basically we've said y equals our intercept plus a slope on type prof times the prof dummy variable plus a slope on type WC times the WC plus error. And if I take away the error, I have to now make this y hat. So this is the model we've fit. And so you can see that like we've converted this categorical variable into these dummy variables. But once it's converted into dummies, it's used in the model in exactly the same way as a continuous variable. This is the predicted change in y for a 1 unit change in prof. This is the predicted change in y for a 1 unit change in WC, and this is the predicted value, the intercept is the predicted value of y when all other variables are 0, right? So who am I referring to? Like, when prof is 0 and WC is 0, we're talking about who? Blue collar, the reference group. Therefore, 35.527 literally is this model's prediction for the blue collar group. Because for that group, this is always 0, this is always 0. So for every case in our data that's blue collar, the model predicts, we predict your prestige is 35.527. It's just making one prediction for that group, right? Now the model also just makes one prediction for professionals. So what is that? Like, how would we get that?
If white collar was 0, so that would be the reference group plus the professional.
Exactly. Because for the profs, this guy is equal to 1, and this guy is equal to 0, right? So the single prediction that we make for this group is 35.527 plus 32.321. Same goes for white collar. They are 0 on prof and 1 on white collar, so they are the intercept plus their slope. So what happens in this model then is that literally these slopes on these dummy variables that are only 0 and 1 represent differences between groups. So 32.321 is the difference between the professionals and the blue collar. And 6.716 is the difference between white collar and blue collar. And it's kind of really easy, once you understand this, to sort of look at this and say, oh, well, I guess the mean of the blue collar group must have been 35.527. The mean of the prof group must have been about, 67, 68? And the mean of the white collar group must have been about 41, 42. And we can just verify that back here when we computed the means of them. 35.527 is the mean of the blue collar group. That becomes our intercept. Now, I know Caddison talked about this, and this is probably revision for you guys, but it's definitely going to be on the first exam. So, and it's important, and it has a lot of extensions, right? Like to start to sort of see any model that you run with R compact notation as giving you this y equals this plus this plus this plus this, and making different predictions for different individuals. The firmer grasp you have of that, the easier like this entire course is going to be. So This is another example from the text for the one-way ANOVA. It's just like a different data set. I don't think this is super important to go through. Essentially, it's just doing the same thing that we just did. So I'm going to skip it. You can also change your reference group. Okay, let's not skip it then, because it's got this other thing. So like, one issue with just looking at these slopes is that they really don't tell us the difference between, well, they do, you can calculate it. They don't tell us the difference between white collar and professional. I mean, you can calculate it, but there's no significance test for that difference. But we're not looking at significance tests yet, but you will. So say we were interested in actually doing a significance test for the difference between white collar and professional, we would have to change our reference group. And this code gives us a way to do that. So maybe I will just update the prestige mod type instead of the Baum model. I'm guessing type, and then we re-level type. And what would I make the reference group if I wanted to test the difference between prof and white collar? Or what are my two options? Exactly. So if I just make the reference group prof, hopefully this works. Now you can see, well, it's a bit convoluted. Professional is now the reference group, so the intercept's gone way up. So the prediction for the model when for the reference group for prof, and now the difference, we've got this significance test for the difference between prof and white collar, -25, and it's significant. But I'm not talking about significance yet, so we don't have to worry about it. Okay, so skipping ahead, any questions before we skip? Cool. All right. So LM can deal with a mixture of factors and numerical predictors. This is called an ACOVA, that stands for analysis of covariance. In the first example, we're not modeling any interactions. So first take a look at the data. We've got scatterplot matrix again. This scatterplot matrix is slightly different because we've kind of asked it, and you'll probably need this skill in an exam. We've asked it to plot the data but differentiate between the groups based on the type variable. So see, we've added this bar type to the code. You will probably need this, even just for this tutorial, but probably for an exam as well. So if I zoom out, what's happened now is that it's kind of the same plot we were looking at before, but now we have this color coding. The key is not there for some reason. Let's see. Ah, there it is. Yeah, so there is a key. I mean, it's obscuring my... Yeah, essentially it gives a different color and a different shape to blue collar professionals and white collar. And so you can sort of look at a plot like this to sort of just have a quick look for any evidence of interactions going on in your data, right? So, for example, we now have separate lines for the relationship between prestige and women for blue collar, professional, and white collar. And it almost looks like there's a slightly different relationship. Like the lines, I think that's blue collar and professional, look negative. The line for white collar looks pretty flat. Could just be noise, could be something meaningful in interaction. So here, for example, the lines, but the relationship between education and women looks quite different for white collar compared to professional. But yeah, just an easy way of looking at your data. So now we're doing a model that includes type and excludes the percent of women. So we're updating the model again. We're subtracting women and we're adding type. To be honest with you guys, I'm not really a fan of the update command. I would prefer it's just to run a new model. and take out what I want to take out and add in what I want to add in. I feel like the less functions you have to memorize and know how to use, the better. Frederick likes it though. I mean, each to their own, right? So let's just use it because it's in here. So we've updated the model, and you can see that we've now got five coefficients, 4 slopes, right? So our intercept is -81. We've got a slope for education. And yeah, literally, so like they all have the same interpretation. They're all the predicted change in y for a 1 unit change in x, right? But when we're talking about the WC and the prof dummy variables, when we say a 1 unit change in x, all we mean is the variable going from 0 to 1. So for example, you would look at this and say, controlling for education and controlling for income, the model predicts professionals to have 6.75 extra points of prestige, just purely based on like that category, right? And that's a much reduced effect than when we weren't controlling for education and income. But that makes sense if you think about it. Because like one of the reasons there's different levels of prestige is related to how much education and income are associated with professions. I mean, this is sort of showing that there's still differences even if we account for education and income. Question?
What do you mean by controlling?
Good question. Well, think about this model, right? So this model's saying y equals, so prestige equals a profession's education level times 3.28 plus an education's income level, logged income level times 7.269 plus a profession's score on the prof variable times 6.75 plus a profession's score on the WC variable times minus 1.43. Exactly the same thing. Y equals this plus this plus this plus this, right? So once you have that model, what you're saying is, okay, if I come in and I make prof go from 0 to 1, have I changed anything about the income level? No. Have I changed anything about the education level? No. So have you heard the phrase holding constant? So holding constant education, holding constant income, this is the effect of prof. That's the idea, is like, this is the prediction. Now we're imagining, so our model, what it's trying to do is say, I'm imagining 2 professions with equal education and equal income, and what boost should I give? What slope should I put on prof when I'm holding constant education and income? So that mathematically is what it's trying to do. It's trying to say, okay, I'm imagining 2 professions. I'm sort of taking education and income out of the equation because I'm imagining them to be equal. Now, what's the difference between professionals and blue collar? And once you hold those things constant, the difference between professional and blue collar in terms of prestige is much lower. But it's kind of interesting that it looks like it's kind of still there, even though it's not significant, but whatever. I mean, what this really shows us is that those things are doing a lot of the work of prestige, not the label, right? Once you control for education and income, whether you call a profession like a professional profession or a blue collar profession doesn't make much of a difference, right? But yeah, so I mean, and that's because like the reason we call something professional is because education and income largely. So really good question. Yeah, and you'll hear it again and again and again in research and in analysis. Or we controlled for this variable. All that means is we fit a model, and what the model said was that even when these other things are equal, even holding constant or holding these other things equal, this is how much our model thinks this other thing has an effect, right? And your estimates can change a lot, right, when you control for things. And that's to do with, like confounding. You can have a relationship between 2 variables that's pretty much all caused by some third variable. So if you leave that variable out of your model, you can see a big relationship between x and y. But once you put that other variable in your model, your model will tell you, well, if you account for this thing, if you hold this other variable constant, there's really no difference in y based on x, in classic cases of confounding. So, great question. So you can estimate the adjusted means. I've spent too much time on this. God damn, there's so much in this tutorial. I'm so sorry. So we're not going to get through everything I wanted to get through, but I'll make another video. Essentially, I'm going to show you guys how to do exercise 2, because it's a really weird exercise. You'll see what I mean when we do it. I can run through it quickly now, but it's something that you will never do. No, literally. Like, it's a pure exercise in coding, and yeah, it's a very strange thing that you do. Like, it's something that you would never do in practice. And I remember giving it to the first year grad students, and they're just like, "What? Like, why are we doing this? This is a really weird thing to do." And I'm like, "Yeah, I know. Like, it's purely just an exercise in can you use R? Can you think about the coefficients of this model in quite a strange way that we're asking you to think about them?" But exercise 3, I want you guys to do yourself. And the tutorial hints kind of tell you how to do it. I think it's pretty easy, but it might require some trial and error. So let's just go through. So this effects package, this stuff you don't really have to worry about. This is just like, these numbers are hard to explain. They're sort of like, these are the means of these professions if we ignore the differences between these professions in income and education, these are the means of the prestige. So you'll notice that 47 is different from 53.76 by exactly the slope on prof, right? So it's exactly 6.75 difference between those two means, but like, they're weird numbers. Like, it's hard to really think about what they mean. There's more detail in the hints document about that, and I show you how to sort of manually get back to those numbers, but it's kind of weird. It's kind of a weird thing to do, to think about that. So objects shows you what objects are in a model, yeah. Okay, so finally we're at exercise 2. So on a separate figure, plot the predictions that one would have obtained for each group without taking the profession type into account. In other words, in the current model, each group has its own intercept. Replace that intercept by the average of the 3 intercepts. What do you see? Okay, so literally, what we're asking you to do is kind of recognize that what this model does by virtue of these dummy variables is it gives each group its own intercept, right? So like, the intercept of the blue-collar group is just the intercept in the model output. But if you think about everybody in the white-collar group gets this boost, right? They get, because they're 1 multiplied by whatever slope we put on the white-collar dummy, right? So it's the same boost for all of them, really. So you can just think of it as changing their intercept. Because all those cases, because they're 1 on the WC dummy, they just get this boost upwards. So we can think about that as giving them a different intercept, right? You don't have to think of it that way. You can just think of it as like it's just boosting them all up by the same amount. But you can think of it as giving them this different intercept. So literally what this exercise is asking you to do is say, okay, well, in this ANCOVA that we just ran, we've got a specific intercept or a specific number for each group where their slope goes through 0 or where their predicted values go through 0. We want you to take the mean of those 3 intercepts and then for each case create a new predicted value, which is just that average intercept plus the slope on education times the education score plus the slope on income times the income score. Yeah, that's the right face, I think, to be making. Like, it's a strange exercise, and I'm just gonna kind of do it and put it in a video, and like, I don't have time to do it right now. Maybe I'll just record the next section and make sure I get to it faster. But then, so ignore that for now. Exercise 3 is relatively easy. Now we're starting to think about interactions, which, oh my god. This needs to be its own section, interaction terms, because it's complicated, takes a while to get your head around. But essentially, this code here on line 155, which for you might not be line 155, Ingram there. How the graphics stuff. Okay. Let's see. This is an interaction plot, and it's kind of a cool plot, just in terms of like trying to understand what an interaction is. What it's doing is every single one of these is plotting the relationship between income and prestige, but it's plotting that relationship for different levels of education. So when education is like at its highest, so 16, we see that there's a pretty, like a kind of a flatter slope between income and prestige. When education is lower, there's a higher slope between income and prestige. This also kind of makes sense just if you think through it in terms of like just conceptually, very highly educated people get prestige even if their incomes aren't that high, right? Less educated people, society doesn't give them as much prestige if they're not earning as much income, right? So like think of some like not super high income occupation that still has a lot of prestige. Like you might say like, I don't know, an adjunct professor at Berkeley, say, right? Like they're not earning that much. They're not earning more than like trash collectors, really. But society tends to give these people more prestige by virtue of the fact that, well, yeah, they still had to study for like a long time. They're still highly educated, even if their incomes aren't that high. So like high education levels, there's less relation. There's still a relationship, but less relationship between income and prestige. Okay, it's one. Essentially, exercise 3, all it asks you to do is sort of reuse this code for a different model and a different interaction and describe it. Oh no, that's not all it asks you to do. It also asks you to use leverage plots and residual plots for that extra model and sort of interpret those plots. And there's actually not that much to interpret. All I really want to see from you guys is get the right plot to print, use residual plots, use leverage plots, and just show me that you understand what those plots mean. But I will make another video that makes all this clearer. And I apologize, but there's just like a lot in this tutorial, and I think like that the stuff we focused on is really important. Like that stuff about like dummy variables, how to interpret them, how we think about using dummy variables to represent categorical variables in regressions. But the interaction stuff, I really want to come back and hit on that more too, because understanding interactions takes a while and is really important. So yeah, look out for that. I mean, I'll post this video and more. I mean, yeah, there's just a lot in this tutorial, but it's not going to be difficult, I don't think. Okay, good luck. Yeah.
Interaction between two variables. Can I say that one variable is the moderator? Sorry, I know you have to get to that.
Well, yes, and it's kind of arbitrary which one you decide is the moderator and which one uses your key IV, because really the model's allowing both things to happen, right? It's allowing x1, the effect of x1 to vary depending on x2, but it's also allowing the effect of x2 to vary depending on x1. So both are kind of happening.
Hi, sorry. I know you're just going to Hildebrand. I'm getting very lost in this. The statistics I know quite a bit about. I did 101, but I didn't have Catters that behind Scott who basically didn't teach coding.
Yeah.
Like,
right.
this much. Do you have any recommendations